Okay, good morning, everyone. Let's get started. So first of all, just reminder, please do homework 3. The workload is pretty light, but it doesn't mean like you should finish it at the last day, right? So if you start early, it will be a lot easier, and you feel much more relaxed, right? Okay, so let us continue with the learning of support vector machines. So in the last lecture, we talked about stochastic gradient descent framework for SVM. And this is our learning objective function. Right? We know that it consists of 2 terms. One term is the regularization term, which reflects our principle to maximize the margin. Right? And the second term is a loss term. Right? This is called hinge loss. Right? It's especially designed from SVM. And this hinge loss, we calculate this hinge loss over every training example, right? Do the summation and to see how well our model fits the data. So if you're doing stochastic gradient descent, we're going to initialize all of our model parameters. So here, just be aware, W includes W0. W0 is the original weight vector and the Bayes parameter B. That's why here we use W transpose Xi, because W has been augmented with the Bayes parameter B, and Xi is augmented with the constant feature 1, right? And then we go through the data set for many epochs. Inside each epoch, you randomly pick up an example Xi, Yi from the training data set, right? And here's the case step. Suppose the original training set contains n examples. So what we're doing is that we're going to repeat the randomly picked example Xi, Yi for n times. So you can imagine that, okay, I'm not going to look at the whole data set. I'm just random pick out one example, but I'm going to repeat that example for n times such that I create a data set which is of the same size as the original data set. And then I compute the objective function on this fixed data set. Okay. And in this objective function, it contains the regularization term, right, which still enforces margin maximization, right? And also, we have a hinge loss on this example Xi, Yi, but because we have repeated these examples for n times, we should multiply its hinge loss for n by n, right? And in this way, we compute the objective function and then calculate the gradient. We use that gradient as the stochastic gradient, then update our model. So as to why we do this duplication, right? We mentioned that because in the objective function, I mean, original objective function of SVM, we include both a regularization term and a loss term. So when you want to compute some stochastic estimate about this objective, you should maintain the scales, right? So you got regularization term here, and you got a loss term over the entire training set. That's the original how the scale of regularization and loss term contrast, right? And when you do this in a stochastic way, you're going to maintain the same kind of contrast. That's the intuition why we should do this. Does it make sense now? I mean, any question about the intuition we explained here? Right. This is different from the least mean square method we discussed previously, because in the least mean square approach, we don't have any regularizer, right? So there's no need to match the skill for additional term. Just have some loss term. So this doesn't, in that case, it doesn't matter like if you multiply your or you duplicate your random sample training example for whatever times. But here, because you have an additional regularization term, then when you construct a stochastic estimate of the original objective, you should maintain the same level of skills for each term. Does it make sense? Any questions so far? Before we proceed to a more rigorous explanation. Okay, so now let us explain why we should do this mathematically, right? We're going to talk about the general stochastic gradient descent framework. Right? Suppose we want to optimize a function where the function contains some regularization term, R, plus a summation over the loss term on a set of data, right? Data points to x big N, right? So how do we use stochastic gradient descent to optimize f of w? I'm not talking about how to calculate gradient, right? If you just calculate gradient, it's just straightforward, right? So now we want to use some stochastic gradient descent approach. Like how can we do that? So first, we're going to rewrite the summation of the loss term in this way. So basically, inside each summation, right, we multiply the loss, every loss term by n, the number of the data points, right? And outside, I multiply 1 over n. So this doesn't change the original loss at all because n and 1 over n just cancel, right? And then, but based on this new form, we can rewrite the whole loss, the whole objective function f of w as an expectation. You can view it, I mean, this term, the n, 1 over n times the summation of n times every loss term, right, as an expectation over n times L, the loss term, over some random data point sampled and its loss, right? And you can view like, okay, I got some uniform distribution over the big n data points. Every time, just randomly pick out one example with the probability 1 over n. And then I calculate that loss. Because your selection of the data points is random, then this loss term, Lxk over W, is random as well. Right? If you take an expectation over this loss term, it will give you the original loss, original objective function. Does it make sense? Right? It's like, okay, I roll a dice, right? This dice has n choices, and I have the equal chance to select every possible point, right? I just random pick out one point, and then calculate the loss over that data point, and I want to look at, because this is random, right? I want to take expectation over this loss, and when you calculate expectation, it's very straightforward. It's just give you this the summation, because every example, every pickup, every possible example xn when it is pickup, the loss will be n times L xn times W, right? And if you take expectation, that means just to do the weighted summation according to the probability, which is 1 over n. That's why you get this one. And this one, we know that it is equal to this one. That is that reduces to the original objective function. Any questions so far? Because this is a very important step. Everyone's comfortable? Okay, so now we can see that we can represent the original objective function as some regularization term R over W plus this hyperparameter C times an expectation. Right? And this expectation is over a loss term of a randomly sampled data point from your whole data set, right? And then because this regularization term is constant to, all those data points, x1 to xk. So you can move this constant R over W inside the expectation, and then we can see that we can represent our original objective F as an expectation over RW plus the C times N times L, the loss over some randomly pick up data point in your data set and W. Right? So now we'll actually give a new viewpoint of the objective function. So the original objective function can be viewed as an expectation of some random objective, right? The randomness comes from, okay, I want to randomly pick up a data point from my data set and compute the loss, right? It's here, right? And then let us look at if you want to compute the gradient of the objective F, what will happen, right? From the viewpoint that F can be represented as expectation. So the gradient of F is the gradient over this expectation, right? So in our case, because the parameters W has nothing to do with the random sample you choose, right? So you can switch the expectation gradient. In other words, the gradient of F is equivalent to, you first compute the gradient of this stochastic objective. This stochastic objective is a regularization term plus C times you random pick up an example from your data set, calculate the loss on that, and multiply with N, right? Then you calculate the gradient, because this gradient is also stochastic, right? So that means you need to take the gradient, you take the expectation over this stochastic gradient, then you can recover the true gradient. Does it make sense? So we call this stochastic gradient as an unbiased estimate of the true gradient. Why? Because you take expectation of the stochastic gradient, it will be equal to the true gradient. And then there's a set of beautiful theories telling us that if you use an unbiased stochastic gradient to perform gradient descent, then as long as your step size is satisfying some conditions, then with probability 1, your stochastic gradient descent will converge to some local minimum or optimum of your objective function. That's why we should use the unbiased stochastic gradient. So basically, if you can compute the stochastic objective function and then calculate gradient, then it is an unbiased estimate of the true gradient. Then you use this unbiased stochastic gradient to perform a gradient descent, then it will guarantee the convergence. So now if we take a look at this wheel, right? So in general, if your objective contains a regularization term and a summation over, a bunch of data points, right? The loss of a bunch of data points, right? And if you want to get a unbiased stochastic gradient, you're going to random pick up an example out from the data set, right? Compute the loss, then multiply with the total number of examples in your data set. Then you construct your stochastic objective, then take the gradient. Right? In this way, you can guarantee that, okay, your stochastic gradient is unbiased estimate. Now going back to SVM case, right? So you can see that we have the same structure. That's why when we randomly pick up an example xi, yi from the training set, we're gonna repeat its loss for n times, right? And then calculate the gradient over this stochastic objective. This is just to guarantee that your stochastic gradient is an unbiased estimate of the true gradient. And then you can guarantee convergence. Any questions so far? Everyone feels comfortable? In general, if you want to do stochastic gradient descent, right, to ensure convergence, you should, every time you random pick up one example, you should duplicate to match the size of the original data set. This will guarantee, your stochastic gradient is an unbiased estimate of the true gradient, and then it will guarantee convergence. Right? That's why we should do this here. This is a step size or learning rate. It's it's like RT or R. We have previously discussed in least mean square method or in the perceptron. Yeah, we're going to talk about how we schedule gamma t to ensure convergence later. It will change. It will change along with t. What? Yeah, in the perceptron case, yes, it's constant. But in general, if you want your stochastic gradient descent to converge, you should make gamma t to vary along with t. Another question? Okay, great. Again, this derivation is not required, and I will want to test you during the final exam. But we list those steps. It's just to deepen your understanding about stochastic gradient descent framework. So almost all the modern implementation of stochastic gradient descent is based on this framework. And we want to let everyone know why we should do this. The reasons that we want to obtain an unbiased estimate of the gradient. And then there are strong theoretical guarantees about convergence. Okay. So this algorithm is guaranteed to converge to the minimum if gamma t is small enough, and also follows some schedule, which we're going to discuss very soon. Okay. So before we proceed, right, you want to give a general comparison between gradient descent and stochastic gradient descent. So what does gradient descent behave? So it's like, suppose this is your optimum, like some minimum of your objective function, right? Those are contours of function values. If you're starting from here, right? So gradient descent always give you some direction pointing to the function optimum. So you run the gradient descent is like you're trying, you have some GPS, right, to guide you directly toward the function optimum. Right? But what's the behavior of stochastic gradient descent? Stochastic gradient descent is like you are a drunk driver. You just randomly drive to arbitrary direction, right? And random drive to another direction, and random drive for another direction, right? So although it looks like every time you're driving randomly and without correct guidance, but amazingly, it will guarantee eventually you're going to still arrive at a home. Right? That's the behavior of stochastic gradient descent. Right? So that also tells us that because you're doing random updates, right? You choose random directions to update the model. If you want to arrive at the same function optimum, you will take many more updates than the gradient descent. But the big advantage of the stochastic gradient descent is that each update is very, very cheap as compared with gradient descent. Remember, if you want to calculate the gradient, you have to calculate the loss over the entire training set, then calculate the gradient, right? You have to go over every training example, calculate the loss, and take the gradient, add them together, you get the correct direction. Right? But if you use the stochastic gradient, typically every time you just need to look at one example, you get some random gradient, right? Random direction. Although that direction is very, very accurate, but it's very, very cheap, right? So that's why in practice, there is some kind of trade-off. Right? If you have a huge number of training examples, and then to get one correct direction using the gradient descent will be much, much more expensive. Then you just pick out one or two examples to get random gradient, right? And as to the total number of updates for you to arrive at the function optimum, although SGD might take many more steps, but if you count the total cost, it might still be cheaper than you use the full gradient descent. That's why stochastic gradient descent is always favored in the large data regime. Okay, so now let us get to the details about how to perform stochastic gradient descent for support back machines. So we actually have some obstacle here. So we have already known our general framework, right? We treat random pickup example xi, yi as a full data set and take the derivative of the SVM objective at current W, right? Then we use this stochastic gradient to update our W and according to some step size t, right? But here there's a problem, right? Actually, our hinge loss is not differentiable. Why is it not differentiable? In other words, we cannot calculate some well-defined derivative or gradient. Right? Why is it not differentiable? Yes, exactly, right? This is a max function. So this is a discontinuous function. It's not differentiable, right? Then how can we calculate the gradient or some substitute for gradient? Yeah, that's one way, but that's not the idea we're gonna share today, right? So rigorously speaking, right, because this max function between two items is not continuous, so there's no gradient, then how can we perform gradient descent or stochastic gradient descent, right? So there could be many approximations. So today we're going to talk about a commonly used strategy is called subgradient. So you can view it as a generalized version of gradient, but it doesn't require the data your objective function is differentiable. Right? So what is subgradient? So it comes from the observation of a convex function. So previously when we discussed about a convex function, we know that at any point, if you draw a tangent line of the convex function, this tangent line will be below the entire convex function body. That's the property of a convex function, right? So what if your convex function, so if you take a look at this, right? This is a blue curve, right? This is a convex function. You at any point, right, you can draw a tangent line. You can see for example, this is a tangent line here, right, with a slope here. And you can see that the entire convex function body stays above the tangent line, right? So then we can consider like, what if my convex function is not differentiable? And remember, convex function is not necessary to be differentiable. And then if you can still draw a line, which we couldn't say is a tangent line because it's not differentiable. But if this line is still stay below the entire body of your convex function, then we're gonna view the slope of that line as the subgradient. So that's the intuition of the subgradient. So let's use one concrete example. So I got a convex function f of x here. So now we know that x1 position at position x1, fx is differentiable. It's continuous, right? But at x2, it's not continuous. And it is not differentiable as well. So at x1, we can compute the gradient of f, right? At x1 and construct a tangent line. We know that this tangent line stays below the entire function body of f of x, right? So the slope is viewed as a gradient, right? But at x2, we're not able to compute the gradient of f at all because f is not differentiable at this point. However, if we can draw a line which passes through x2 and f of x2, and this line still stays below the entire body of f of x, then we will the slope as a subgradient of f at x2. Does it make sense? Right? So formally, g is a subgradient to f at x if the whole function body, you can see that f, y is vary along the whole domain, right? Is no less than the line which has slope g and goes through x and f of x. This is kind of a formal definition, right? So geometrically, it just means if you can draw a line which passes through this data point, this point at f, but then the other part of this line stays always below the entire body of fx, then the slope of this line is called a subgradient. Any questions so far? Is everyone clear about definition? Okay. So actually we can see that at the same position like x2, right? You might have many subgradients. Can you speak a little bit louder? F here we require it to be convex function. Yeah. F is convex. And then given that f of x is convex, then at any point, if we can draw a line which still stays below the entire body of f of x, then the slope of that line is called a subgradient. It actually was motivated by the observation that, okay, if f is differentiable, then its tangent line stays below the entire function body. Now we kind of relax this requirement that, okay, as long as you have some line past one point at your function body, but then stay below the entire function body, then that slope can be used as a subgradient. It's called subgradient. Any other question? Everyone's comfortable about the definition? Okay, that's great. And good thing is that in the optimization of a convex function, if you use subgradient to perform descent, you're going to still guarantee convergence to the function optimum. That's why we can pick up subgradient to replace the gradient when the function is not differentiable. Okay. And we can see that at some point where your f is not differentiable, you could have many different subgradients. Right? And in that case, you can just pick up whatever subgradient you like and perform the subgradient descent. Any questions so far? Okay, so now let us try to construct a subgradient for SVM objective. Right? We know that SVM objective is not differentiable because of this hinge loss. This hinge loss is a max function, right? So let's see what kind of subgradient can we find for this max function, right? So this is the shape of a max function, right? If the input, this is 1 minus function margin, right? Is bigger than 1, then it is 0, right? It's here. However, if the function margin is less than 1, then the max of 0 and this 1 minus function margin will be 1 minus yi w transpose xi, which is line, right? So obviously, I mean, we can pick up very easy subgradient. Right? First, if this max function value is simply 0, I mean here, then we can just use 0 as subgradient, right? Right? And that's the first case, right? If the max function is 0, right? That means it is in this part. I can just draw a line which has 0 gradient, 0 slope as well. So know that, okay, this line will stay below the entire max function body. So that means this part will simply be 0. You take the gradient, you mean with respect to w, and this part because 0, so it's the gradient 0. So you only need to take the gradient with respect to the first term, right? So it's just the w0. And in the second case, is that okay? Your max function value is not 0, is here, right? It's here. So then let me just take the gradient of this line, right? Or take the slope of this line. I use that as my subgradient. And this is a value because we know that if you draw a line which overlaps with here, right? You know that the whole line still stay below the entire max function body. In that case, you take the gradient with respect to w, which will be c times n times minus yi xi, as here. And the gradient for the first term, it doesn't change. It's still w0, 0. So now we can see that we have constructed one version of the subgradient for the SVM objective, right? We just need to look at, okay, what is the value of this max function, right? If it's 0, you just pick the line with 0 slope. And if it's not 0, you just pick a line with this slope, right? And of course, you can have many other choices. For example, you can calculate, you can draw a line here, right? And then calculate the slope of this line as a subgradient as well, right? It's up to you. But here we just pick up one most naive, most straightforward subgradient. Any questions so far? Okay, so next, let us just integrate this subgradient into our stochastic gradient descent framework for support vector machines, right? That is called stochastic subgradient descent for SVM, right? So this is our stochastic subgradient for SVM, right? So the whole framework is as follows. Given the training set, given the binary label -1 and 1, right? We initialize our model parameters as 0. Then we go through the data set for many epochs. Then inside each epoch, we go through every training example, xi, yi. And then according to the value of the max function, the hinge loss, right? We're gonna pick up different subgradient, right? So here, when the function margin, yi w transpose xi less than or equal to 1, we know that this 1 minus function margin will be positive. So max function value will be non-zero. So that means we're gonna use this guy as the subgradient, right? That's where then we inject it into the gradient descent update. That's our updating. Right? And when the function margin is bigger than 1, we know that max function value is 0. So this is a subgradient. And accordingly, you update your model parameters in this way. Okay? And you finish one update, you go to the next example, and you do the stochastic subgradient computation again and update our model parameters accordingly, and do this again until you finish each epoch and until you finish all the epochs, right? And eventually you're going to return your model parameters. And here gamma t is the called learning rate, right? There could be many possible tricks we're going to discuss in a minute, right? And also in practice, to ensure your pick up training examples are randomly enough, in each epoch, we're going to random shuffle the training set. So that means you're going to have a different random order of the training examples to deal with. That's the whole framework when we implement our, we use to implement our stochastic subgradient descent for SVM in practice. So any questions so far regarding the algorithm steps? I believe it's straightforward, but because everyone will follow this framework to implement your SVM version, so I want to make sure that everyone feels comfortable and no doubt about this. Okay, great. So the last question we want to talk about, how do we schedule gamma t? Right? So as we previously discussed, right, gamma t is very important to guarantee convergence. And actually, in practice, we need to make a smart schedule of gamma t to ensure convergence, right? So what kind of gamma t schedule should we use? Right? So here is the theorem. If the step sizes, namely gamma t's, are square summable but not summable, then in theory, with enough iterations, our stochastic gradient descent will converge in expectation, meaning that with probability 1 or almost sure. Right? So what does it mean for square summable but not summable? So it contains 3 points, right? First, every step size must be positive, non-zero. Second, if you just compute the sum of squares of the step sizes over t from 1 to infinity, and this summation must be bounded. It should not diverge. This is called square summable. So that means I just take the square of every step size. I just sum over them from 1 to infinity step sizes, right? This summation must be bounded. And third point is that if you just sum over all the step sizes from 1 to infinity, then it must diverge. It shouldn't be bounded. So what does it mean? What does this those conditions mean, right? So we know that. So suppose this is your objective functions landscape, right? So you're starting from some point here, and this is where you want to arrive. Right? When you run your stochastic gradient descent, right? If your step size is too large, what will happen? Right? It could be just fluctuate. Right? If it is too large, there could be cases where you just fluctuate and never converge. I mean, jumping back and forth at some level of this valley, but you won't go further down. To avoid that situation, we require that the sum of the squares of the step sizes should be bounded. That means the step size should not be too large. Let me write it in a more concise way. 1 to infinity, your gamma t square should be bounded. So this condition just requires you requires your step size schedules not to be too large. And if it's too large, there could be the case that you just fluctuate, jump back and forth, and never arrive at the optimal. But what if the step size is too small? What is the possible consequence? Any thought? What if the step size is too small? It's like you don't have enough gas to arrive at your destination. I remember, like, if you want to drive to Las Vegas and your gas tank is only 12 gallons, right? You have to stop in the middle, maybe in St. George. I'm not sure if you can drive to St. George with only 12 gallons, right? And you'll never be able to move forward. Right? That's their step size is too small, right? If your step size is too small, it's like, okay, you just update, and at some stage, your move forward is too small, right? You'll never be able to arrive at the local min. That's why, to avoid this situation, we should add additional situation that the summation of step size itself must be infinity, must be unbounded. If you write it down, it's like this one. Gamma t is infinity. That is just to avoid. That's just to tell you that, okay, you must make your step size to be large enough so that it won't stop in the middle. So you can see that we have two conditions, right? One condition is to make sure your step size is not too large, such that you just perturbate and never arrive at the destination, right? And the other is to make sure the step size is not too small, so that you just stop at the middle. And if you can come out with a schedule which satisfies those conditions, then with probability 1, your stochastic gradient descent will arrive at some optimum of your function, objective function. Like more rigorous speaking, it should be called attraction basin. Right? But anyways, it doesn't matter. And there are a lot of schedules which can satisfy those conditions. Here we just give two very simple schedules. Right? One is that you're going to specify some constant A is positive. You specify some initial step size gamma 0, which is positive as well. And then you just update gamma t in this way. Right? Or even simpler, you can just start with the initial step size gamma 0 and then divide by 1 plus t to get your gamma t. And both schedules satisfies the conditions here. Okay, any questions so far? Great. So here are some like theoretical results for us to better understand when stochastic gradient descent is more advantageous and when the gradient descent is better. So suppose we want to know how many iterations or updates shall we need to get to an accuracy within epsilon. That just means the distance between your learned model parameters and the optimum is within epsilon. We would like to know how many iterations in scale do we need when we run gradient descent or stochastic gradient descent. Okay. If your objective function is strongly convex, let us just forget about what is strongly convex. Like, suppose we have n training examples, we have a d-dimensional, meaning that the input feature vector is d-dimensional. Then the gradient descent will need this many iterations or updates to arrive at an accuracy within epsilon. So you can see that the number of updates or iterations is proportional to the size of training data, right? And the dimension of the input feature vectors and logarithm of 1 over epsilon, the designated level epsilon, right? And but for stochastic gradient descent, the convergence, the number of iterations has nothing to do with the size of training examples. It's just proportional to the dimension of the feature vector and over epsilon. Now we can observe that why stochastic gradient descent is more favored for large data, because it doesn't rely on the data size. But for the gradient descent, if n is relatively small, right, and because the number of iterations is just proportional to logarithm 1 over epsilon, so actually you can expect to be very small, right? The whole total number of iterations, right? When n is small. However, if n is super large, the number of iterations or updates required for gradient descent will be super large as well, right? But for stochastic gradient descent, it doesn't matter, because the size of data set n has nothing to do with the number of the iterations required to arrive at accuracy within epsilon. That's why when data size is huge, we prefer stochastic gradient descent, because we do not need to worry about data size, about convergence. Any questions so far? Okay. So now we have finished the introduction about SVM training using stochastic gradient descent framework, right? So we need to be aware two key points. One point is that in the SVM training, every time we pick a random example, we need to repeat it, right? To construct a fixed data set to be of the same size as our original data set, to make sure that your stochastic gradient descent is unbiased, because unbiased stochastic gradient will ensure convergence. And second thing is that you actually cannot compute the gradient. You have to use some subgradient, because the hinge loss is not differentiable. Okay, the last thing we want to discuss is about the comparison between SVM and perceptron from the optimization perspective, right? So this is our stochastic subgradient descent for SVM. We know that according to the value of the function margin, we can decide which subgradient we're going to choose to update our model parameters, right? So now if we compare with perceptron update, we just need to change this if-else statement by the updating rule for the perceptron, right? So for the perceptron, it becomes, okay, I'm just look at my function margin, yi w transpose xi, right? If it's less than or equal to 0, we know that it updates, it makes mistakes. Then I follow my perceptron rule to update w, right? If it is bigger than 0, that means, okay, you make a correct prediction, your update, you don't need to update anything. In other words, you can view like your stochastic, your gradient simply 0. Right? This analogy or this contrast might motivate us to think about, okay, because the whole procedure, right, for SVM stochastic training is very similar to the perceptron update, right? The only difference is the updating rule. Then we can think about that. Is there any hidden stochastic objective function, stochastic subgradient framework also applies to the perceptron? Okay. In other words, can we view the perceptron updating rule as doing some stochastic subgradient descent as well? If that is the case, then what is the objective used underlying the perception? In fact, it's not hard to construct such a loss or such an objective for perception. Right? If we construct an objective function for perception as follows, that is, we take the maximum between 0 and minus function margin, then we perform stochastic subgradient descent to optimize this loss. We're gonna exactly recover our perception update. It still takes two possible subgradient, right? When the max value is 0, then your subgradient is 0. That means you don't do any update. Okay? In that case, your function margin is positive. Right? In other words, on the other side, like if your max value is minus y w transpose x, that means this function margin is negative. Then you take the subgradient by taking the gradient of the right term here, it will give you the updating rule of the perceptron. So now we can give even more unified and generalized view of the perceptron learning, right? Perceptron essentially is performing stochastic subgradient over another objective function. And the difference from the SVM is that SVM has this hinge loss, right? It's max between 0 and 1 minus function margin. And perceptron has a different loss, which is max between 0 and minus function margin. So there's just a get rid of this constant 1. And it doesn't have the regularization term for the weight vector. That is a perceptron. And hopefully this view can give us a different understanding about the perception. Although it was motivated by some intuition, right? Once I made a mistake, I update the model. Otherwise, I don't need to make any updates. Right? But in a high level, you can still view it as optimizing some different objective function. Okay. So in summary, from the optimization perspective, SVM essentially is to minimize a regularized hinge loss. Remember, the objective function for SVM contains two terms. One term is the regularization term that penalizes over complex hypothesis space and encourage large margin, right? And the other term in the loss is a hinge loss, which measures how well our model fits the training data. And we can use stochastic subgradient descent to solve the optimization problem. It has a benefit of being very fast, and the runtime does not depend on number of examples. And we have some analogy with the perceptron algorithm. In other words, perceptron can be viewed as optimizing a little bit different objective function using stochastic subgradient as well, right? And another difference is that perceptron does not maximize the margin, right? But stochastic subgradient descent is not the only way to optimize the SVM objective function. There are also other successful optimization algorithms, such as dual coordinate descent and liblinear. Right? In other words, one of the most popular support vector machine packages. Right? Okay, any questions so far? Everyone's comfortable? Okay, great. So now we have finished the discussion about training SVM in the primal domain. Next, we're going to talk about how do we generalize support vector machines to nonlinear classifiers. Okay. To flexibly extend support vector machines for nonlinear classification, we have to consider how to optimize support vector machines objective function in the dual domain. And in the dual domain, we're going to introduce the so-called kernel trick. So you can view it as doing some implicit feature mapping to higher dimensional space, to latent high dimensional space, and do the optimization. Right? And performing all this requires us to understand what is the dual optimization problem. Right? So in the discussion subsequently, we're going to introduce several basic concepts in the optimization and introduce a bunch of new concepts. But overall, it is not hard. It just consists of a series of logic chains. And you're not required to memorize this. We just ask you guys to understand the logic, the reasoning, and how we derive from the primal objective to the dual objective, and how we perform kernel trick in the dual objective. You'll see that when you derive the optimization problem as the dual form, it is very straightforward and intuitive to apply the so-called kernel trick. Okay, so here is our plan. So we're going to first introduce dual forms for general constraint optimization problem. Then we're going to apply the dual form for the support vectors. And usually, the solution solved from the dual form is different from solution solved from primal form. But for support vector machines, because it's nice design, it's a convex optimization problem, so the solution of dual is the same as the solution of the primal. Then we're going to talk about kernels and kernel trick, properties of kernels, and then we're going to discuss how we directly inject the kernel trick into the dual form of the support vector machines. And you will see that by solving the dual form, it is essentially to solve the learning of linear classifiers in a very high dimensional latent feature space. Like in that way, we can perform nonlinear classification. Okay. So first, dual forms, right? So far, we have seen support vector machines, hinge loss, optimizing the regularized loss, right? More broadly, we have seen different algorithms for learning a linear classifiers. But linear classifiers, we know that it's still kind of limited in the expressivity, right? What about we want to learn some nonlinear classifiers? So previously, actually, we have discussed the idea about how do we adjust a linear classifier to handle nonlinear classification case. Can anyone recall what kind of trick can we use? Any thought? We can perform some feature transformation, right? So here, hopefully this picture can make us recall something, right? So we know that in a two-dimensional space, those blue rectangles, blue squares, and the red circles are not linearly separable, right? We cannot draw any line which can well separate them. And how do we obtain a good linear classifier to well separate them? One idea is that, okay, I'm gonna introduce additional features to re-represent every data point. Okay? For example, for every example, x1, x2, right? I'm adding additional two features, x1 squared and x2 squared. Then every example can be represented by a four-dimensional feature vectors, right? And then you place, it is like you place these data points in a higher dimensional space. And in that case, we know that all those points can be well separated by a hyperplane, right? So then we can try to find a weight vector in this higher dimensional space and find out the weight vector and the bias parameter, and we can still expect that in the higher dimensional space, a linear classifier can do their job very well. So that's the idea, right? So now, let us look at the primal and dual forms for support vector machines. We start with a general constraint optimization problem. Suppose we want to minimize an objective function f with respect to x and subject to a set of m constraints. So those constraints are represented by inequalities like g1x less than or equal to 0, g2x less than or equal to 0 until gm of x less than or equal to 0. So here we do not assume like f and g1 to gm or convex. No, it doesn't matter. F, we can just assume f and g are arbitrary functions. Right? Associated with a general constraint optimization problem, we can construct a so-called Lagrange function. So what is Lagrange function? Right? You just add the objective f plus a linear combination of the constraint function. So each coefficient lambda I is called a Lagrange multiplier. So this form or this new function is called Lagrange function. So why do we construct a Lagrange function? We can convert this general constraint optimization problem into a minimax optimization problem over the Lagrange function. In other words, solving this constraint optimization problem is equivalent to solving this problem. So this new problem is to do the minimax optimization over the Lagrange function. So in the inner level, we're going to maximize the Lagrange function with respect to the Lagrange multipliers. In the outer level, we're going to minimize the Lagrange function with respect to x. And here, we have a non-negative constraint over every Lagrange multiplier. Namely, lambda 1 to lambda m must be non-negative. So what's the benefit of this minimax optimization as compared to the original general constraint optimization problem? Any thought? Any guess? The biggest benefit is that your constraint is only non-negative constraints, right? It's much, much simpler than the constraints specified in the original problem. In the original problem, actually the constraints specified by this g1x less than or equal to 0 until gmx less than or equal to 0, right? You can imagine if g1 to gm are complex functions, right? Actually, your constraint space can be very complicated. But here, when you convert it into a minimax optimization problem, your constraint is just non-negative. It's just the cubic. That's one major benefit of doing this. So for simplicity, we can rewrite this minimax in this way, right? We want to minimax the Lagrange function where in the inner level, we have a non-negative Lagrange multipliers to maximize L. And in outer level, we want to minimize the Lagrange function with respect to x. And x does not have any constraint. So any question regarding the second formulation? Everyone feels clear and comfortable about the second formulation? Okay, great. And then I want to answer why. Why we can convert this primal problem into this min-max optimization problem, and why the two problems are equivalent. So to see this point, right, to see why they are equivalent, right, let us look at the min-max optimization problem. More specifically, let us assume x is fixed, right? Let us just look at the inner maximization. The inner maximization of the Lagrange function, what value it will be, right, for different choice of x. First, if x satisfy all the constraints, what is the maximum of the Lagrange function? Right. For any x, right, if it satisfy all the constraints in the original problem, namely g1x less than or equal to 0, g2x less than or equal to 0 until gmx less than or equal to 0, then you maximize the Lagrange function. What will be the maximum? Or in other words, what choice of lambda value should you use to maximize the Lagrange function? Any thought? We can observe that the Lagrange function is f of x plus the linear combination of those constraint functions, right? Because x satisfy all those constraints, that means each evaluation of those constraint function over x is negative, right? Now I want to maximize this value. What lambda I should I choose? Simply 0, right? Remember, lambda I must be non-negative, right? It cannot be negative. So if you pick up if you pick up a positive lambda, right, you kind of like subtract your objective f of x by some positive value, right? You don't want that happen, right? That's why I should pick up lambda i's to be all 0. Right? And what if x, I pick up x, which violates any of those m constraints? If that's the case, what will be the maximum value of the Lagrange function in terms of lambda? Think about it, right? So suppose I got g1x is bigger than 0, right? That just means your x you chosen is violating the first constraint. So g1x is bigger than 0. Now in my objective function, I know that I multiply lambda 1 with g1x, right? I want to maximize the whole Lagrange function. What lambda 1 values should I use? I heard that. Infinity, right? Because I want to maximize the whole function with respect to lambda, right? I know that, okay, one factor that lambda multiplies to is positive. Now I want to increase my function. I want to make my function value to be as large as possible. Just pick up my lambda to be infinity. Then that gives us the second observation. If x violates any constraint, okay, then your inner maximization will lead to infinity of the Lagrange function, right? Does it make sense? Okay. On the other hand, if your x satisfy every constraint, that means every constraint function is is negative or 0, right? Then to maximize your function, you should pick up every lambda I value to be 0. Then your inner maximization will reduce to f of x itself. Okay. So now, if we further do minimization over x, that's our minimization problem, right? We can auto level, we do minimization over x, we can see that it is equivalent to minimize f of x when x satisfies all the constraints, or minimize infinity, right? When x does not satisfy the constraint. Okay. Of course, if you do a minimization, infinity won't be your final optimum, right? So the result will be the minimum of f of x where x satisfies all the constraints. This is exactly what the original constraint optimization problem does, right? That explains why the minimax optimization problem is equivalent to the original general constraint optimization problem. Does it make sense? Any question? Okay, if you feel a little bit uncomfortable or you didn't catch up with this, it doesn't matter. Right? Just look at the slides for 10 more minutes, you'll get it. But here I just want to slow our pace to make sure everyone feels comfortable about that. This is a very simple logic reasoning here to explain why converting the original problem to this minimax optimization problem is equivalent. Right? So basically, the key observation, let me repeat again, right, is that you maximize the Lagrange function with respect to non-negative lambda, right? Will give you two results. When x satisfies the constraint, it will just return to the original objective f of x. When x doesn't satisfy all the constraint, it will just give you infinity. Then you do one level alter minimization over x. It just give you the final result will be okay, minimizing fx where x satisfies all the constraints, because your value won't be infinite. And we can see the benefit here, right? Although we introduce two-level optimization, right? We have to do mini max, right? We have to optimize x also lambda. The benefit is first, I greatly simplify the constraint. Now the constraint is over the Lagrange multipliers lambda only, and those are non-negative constraint is just a box constraint. Right? And second, I completely get rid of the constraint over x. X is free. I don't need to worry about if x really satisfies the constraint or not, right? Because doing this minimax optimization, essentially all the meaningful solutions will be the x that satisfy the original constraints, right? And following the same framework, it is very trivial to incorporate equality constraints as well. That is, suppose I want to minimize an objective function such that g1x equal to 0, g2x equal to 0 until gmx equal to 0, and you can reformulate as the same kind of minimax optimization problem, right? But it's a little bit different. So I will leave it as an exercise for you guys to do that, like deepen our understanding. And we all know that when we do the calculus, maybe in high school, we learn how to solve the constraint optimization problem, right? We just construct the Lagrange form and take the gradient and solve the gradient being 0, right? And now, from what we have discussed today, we see that solve that problem is not maximization or minimization. They're essentially solving a minimax optimization problem. So after some kind of conversion, right, we got our minimax reformulation of the objective function. We call it primal form. So the primal form is to doing inner maximization over the Lagrange function with respect to non-negative multipliers lambda. And in outer level, we do the minimization of the Lagrange function with respect to x. This is called the primal form. If we switch the order of max min, namely that we first do the inner minimization of the Lagrange function with respect to x, then in the outer level, we maximize the Lagrange function with respect to non-negative lambda, then it is called dual form. So you can see the only difference is the order of min and max. So now I want to ask, will the solution of dual form be the same as the solution of the primal form? In other words, if I just switch the order of max and min, will the solution change? Just give me a guess. What's your intuition? Will it change or not? Come on, there's no punishment. What's your guess? It'll stay the same? Yeah, that's my intuition as well, but that's wrong. If you change the order, in general, it won't stay the same. In general, the solution, the optimum, if you evaluate the Lagrange function at optimum of the dual, it will be less than or equal to your evaluation of the objective or Lagrange function at optimal or primal. And this is a mathematical equations which expresses the conclusion I just said. Right? And there are a bunch of derivations. It's really simple. I'm not gonna go through the details. It's just for your reference if you want to like to know why. And here we just list the reason here. But general, the solution, the optimal of the dual is less than or equal to the optimal of primal. But the good thing for SVM is that for the SVM, the solution of dual is the same as solution primal. And in the next step, we're gonna construct the dual form of SVM and see how can we simplify the dual form to a quadratic optimization problem for SVM. Okay, yeah, let's stop here today and see you on Thursday.